Okay, recording has started. Share the screen. There we go. Can everyone see the title slide? Radiated emissions electric field RE102.
Yes.
All right, so welcome to the latest session here on RE102. And here is a list of the topics that I'll be talking about for the next hour plus. So we'll start out with what I call the raison, or what the French call the raison d'etre of RE and RS. So the raison d'etre of RE02 or RE102, radiated, specific to electric field here, is to protect antenna connected radio receivers from emissions coming from your box, where your box is the culprit. You're bringing your box to test. It's all about protecting an antenna connected radio receiver from you or from your equipment. So the raison d'etre of RS103, the radiated susceptibility electric field, is to protect your equipment from emissions from radiated energy coming from intentional antenna connected radio transmitters. Okay. It is not correct or valid to directly compare these limits. That is not in any way, shape, or form what is intended here. Square pegs and round holes, whatever metaphor you like, but this is not what you are supposed to do with those limits. The way you have to think about this is that a properly defined radiated emissions limit, well, it's all about protecting specific radio receivers or receivers that may be used by your equipment. So a little bit of context here. When we're basing our test programs for NAS emissions on Mil Standard 461, well, it is a military standard, right? So this is where we have to be a bit mindful about how we're applying it. Because with NAS emissions, they tend to be kind of onesie twosie types of emissions, where military platforms are less so. So if you think of it as like you're a contractor, a vendor of some widget, let's say a transponder. Just about every mission is going to use a transponder of some description. So if you're a vendor of a transponder, you're not gonna make your living selling one transponder to one mission. You want to make many copies of that transponder to fly on many different platforms. So in the military universe, just using my imagination, I mean, I spent my whole career here with NASA, so I'm having to just kind of use my imagination on the military side of things. But I can just imagine that if I'm providing a transponder or whatever device it is, but using a transponder as an example, I want to sell a whole bunch of these things for the military to fly on a lot of different candidate platforms. So the context of applying the Mil Standard 461 to my approach to testing my transponder is that, okay, if you want to be able to fly on any military platform, you have to meet this radiated emissions limit, this RE102 limit, across the board, across the whole frequency spectrum. And then if you comply with that limit, then okay, you're basically okay to fly on any candidate platform. I mean, painting with broad strokes here, but I think that's the general approach for in that kind of context, where in NASA missions it tends to be more onesie twosie, as I said. So you have much more specific RE102 limits to protect specific radio receivers. So it's much more mission specific. So the context is quite a bit different. Okay, so but the entire point is that a properly defined radiated emissions limit, an RE102 limit for electric field, is all about protecting radio receivers. And RS103 is all about protecting you from antenna connected radio transmitters. Apples and oranges, they're serving very different purposes. So please don't do this with them. I hope I'm being clear here. Not a whole lot of ambiguity here. So, okay, so next chart here is just quoting chapter and verse from the mill standard, underscoring what I just said. And then another statement here, it may be desirable to tailor the frequency coverage of the limit to include only frequency bands where antenna connected receivers are present. Now, this is generally above 200 megahertz for Goddard platforms. So that is our default in GEVs, is that we apply RE102 only above 200 megahertz. And again, this is a common refrain here. But the cables are part of the EUT. Again, quoting right chapter and verse from the mill standard. And this is all in the appendix, by the way. I'll say over and over again, there's a lot of very, very valuable information in the appendix. Anything that, any section number in the mill standard starting with A, that is in the application guide appendix. And the remaining part of that section number just refers to the section in the main body of the document to which it applies. So 518 is RE102, and then A518 is the discussion in the application guide that provides a lot of this type of information. So anyway, just the cables are part of the EUT. It's very explicitly stated in the mill standard. So reviewing a few things here, we can go through this pretty quickly. So just this I covered in the overview section. But interconnecting cables, again, are part of the EUT, and properly designed box level test with flight representative cables as they're required to be, and representative loads exercises the cables as much as the electronic box. And here's the general setup diagram for GEVs. It's a tailored version of the corresponding diagram in the mill standard. Main difference is just the capacitor network instead of LISNs. But it defines a specific configuration for interconnecting cables, in particular for radiated testing, right? Because the common mode currents that can couple onto these cables will produce radiated energy, and then incident radiated energy can couple onto these cables that can be carried into the EUT. Again, just for review, when an EUT meets the stringent RE and RS requirements on a military platform per the mill standard, there's generally a low risk of crosstalk. So that default RE102 limit from the mill standard corresponds to common mode current levels that are generally too low to pose a significant risk of crosstalk. Okay, so this is one of the big reasons that RE102 exceedances have historically been the largest source of waivers on many Goddard platforms. And most Goddard platforms do not use antenna connected receivers below 200 megahertz. So following this guideline, the default is we only apply RE102 above 200 megahertz on Goddard platforms. If you do indeed have a radio receiver operating in that frequency range, then which we do occasionally, then by all means you need to test there. But if not, the default is we treat the dominant concern below 200 megahertz is crosstalk. We've covered that in the last couple of sessions on common mode emission, conducted emissions, and susceptibility. And I love this quote from late great Henry Ott: "Conducted emissions limits are really radiation with radiated emissions limits in disguise." So getting to the RE102 test method, we've hit on this in some previous sessions, but one of the key points here is the test antenna is placed 1 meter from the test setup boundary. This is one thing that's a non-negotiable. There's a lot of tailoring that's permitted and encouraged, but in this case, the 1 meter measurement distance is very specific and non-negotiable for RE102. And I'll talk a bit about why here shortly. But we have an antenna configuration break at 200 megahertz. We're using this biconical or bow tie antenna from 30 megahertz to 200 megahertz. So just because we have an antenna configuration break at 200 megahertz, that just lends itself nicely to, okay, we will just apply by default anyway, apply RE102 only above 200 megahertz. So again, the dominant concern below 200 megahertz is crosstalk. That 1 meter measurement distance is not really useful when to address crosstalk, because you're almost always more concerned about crosstalk for cables that are much closer together than that, on the order of a couple centimeters. And just any attempts to correlate the measured field at 1 meter to an expected field at a few centimeters is really not something you should do. Non-trivial is putting it too mildly. I probably should change the chart, but it carries very large uncertainty. It's just not really a meaningful thing to do, no matter how many times people try it. So it's more efficiently addressed with direct measurements of common mode currents. Okay, and that's what we talked about in the last couple of sessions. Okay, so that kind of reviews stuff we talked about. Now we're going to plunge into RE102 proper. Does anybody have any questions before we get more into the meat of this? Okay, I think I was hearing a hot mic, so if you can please mute when you're not asking a question. Okay, so here are the three basic antenna types. We have the rod, the biconical, and the double ridge guide horn. I'll talk about each of these in turn here. But this diagram is right out of mill standard, and so one beyond the 1 meter measurement distance, we already hit on that. But the height above the floor is specified as 120 centimeters, 1.2 meters, however you prefer to think of it, but it says 120 centimeters here. And then there's a little note down here, may be adjusted to meet the area beam width requirements in the cited sections of the document there. And sometimes, like the biconical, it's a large antenna, so in vertical polarization, the base of it can get very close to the floor. So you know, may want to adjust that a little bit as needed, but we want to get to that 120 centimeters as closely as you can. So the rod antenna, or it's also called a monopole, it's specifically cited as a 41-inch rod antenna. That operates in the lowest frequency range, 10 kilohertz to 30 megahertz. A typical model number here, ETS Lindgren 3301C, active monopole. So yeah, active monopole is I think that's the official name for it. And rod is a little more colloquial. But it like any monopole antenna, any antenna needs some reference, right? If it's not a dipole, a monopole still needs a reference, and that's the counterpoise or ground plane. You know, or I mean, it's called the counterpoise, so it's a small ground plane, right? Ideal ground plane is infinite, but this is a manageable size here to provide the reference for the monopole antenna. Rod antenna measurements are I'll just say, just parenthetically here, one of the first talks that I recall going to at the EMC symposium when I first started going 14 or 15 years ago now, was a session on rod antenna measurements that seemed, you know, it initially seemed like it was going to be a very dry subject, but then when we got to the question and answer period, things got very lively, and passions were excited pretty significantly. Harry, are you on? I don't know. Harry from JSC. Well, you know him, you know who I'm talking about. Harry got up to ask a question, and he definitely livened up the discussion. So it's just, anyway, that's all I'm going to say about that. We don't generally use the monopole because it's down in this low frequency range, but there are still occasions where we do use it. So we'll talk a little bit about these antennas on Wednesday, whenever we can do the lab portion of this, and I'm hoping we can set up to do it Wednesday. And I'll show you the antennas that we have at Goddard, and then some of the nuances about how to use each one. So the 30 to 200 megahertz range, we use the biconical, or it is sometimes colloquially called the bow tie antenna. I'm not making that up. It is sometimes called a bow tie, but the official term is biconical. Typical model. You notice ETS Lindgren is a pretty common name here. They're kind of the industry standard for test antennas. So the 3110C. So these two are just not generally used in favor of common mode conducted emissions measurements below 200 megahertz that we've discussed. Well, and when we get to the nuances of these, I'll just give you a sneak preview. The biconical antenna really it can be very problematic to use. It's very inefficient at the low frequencies. So from 30 hertz up to, I think, maybe 80 to 100 megahertz, it's just extremely inefficient. It just has a lot of losses associated with it and things like that. The other point is in this frequency range, so 30 megahertz has a wavelength of about of 10 meters, and 200 megahertz is a wavelength of about 1.5 meters. Kind of sounds about in the range of dimensions of a typical EMI test facility, right? I mean, it certainly is right in the zone of our small lab anyway. And anechoic material is not terribly effective down in that frequency range. The anechoic materials tend to be more effective as you go up in frequency. So the point is that reflections, constructive and destructive interference are very much a likely thing you will have to deal with in that frequency range. And I've definitely experienced that. There can be a lot of complications in that frequency range if your facility is not very well controlled, and it's really hard to control reflections in that frequency range, certainly at the lower end. So anyway, you'll need to know these nuances if you ever have to use that antenna, but by and large, we want to just go with our common mode measurements below 200 megahertz. Now the antennas that we do use still on a regular basis, they lump everything above 200 megahertz in, they just, in the document, they just lump it all together as a double ridge horn. Well, there are two different ones to cover different frequency ranges. There's the large double ridge guide horn, or DRG. Sometimes you'll just hear it called DRG, so you'll need to know what that means. So from 200 megahertz to 1 gigahertz, and there's ETS Lindgren again, the 3106B. I should mention that with I think more or less all of these antennas, you can other vendors have provided these over the years. I think you can still go to other vendors, but those model numbers are pretty universal. You can get a rod or a biconical antenna from another vendor, and they'll still tend to use these numbers here, and that's true for some current probes as well. So that is one kind of cool thing in the EMC test equipment industry is somebody else may make a 3110C antenna, and they'll still just use that number, so that it's equivalent to this. It's not vendor specific. And then above a gigahertz, there's the small double ridge guide horn, or DRG. Typical one we use is the ETS 3115. And that's a roughly, rough order of magnitude relative size comparison here. The large DRG is pretty large. If you've ever seen it, you know what I'm talking about. It's about a meter wide, maybe a bit wider, between 1.5 meters wide. It's a pretty good sized antenna. Then this one's is much smaller and more manageable. So polarization. So if you're looking right into the snout of one of these antennas, any antenna has two conductive elements. Even that rod, the monopole, it has the main conductor and then its reference, which is the counterpoise. But these DRG antennas, they have your two conductive elements, right? And then that's what produces your radiated field. If you're thinking of it as a transmit antenna, right? You're feeding a signal into the connector that's on the other side here that you can't see, and you're providing or producing a potential between these conductive elements, and that produces a radiated field. And the direction that's in line with the two conductive elements is called the E plane, and then the orthogonal to that is what's called the H plane. So you'll see those terms in antenna data sheets, and we'll look at antenna patterns and things like that. That's what that means. Okay, and then so then horizontal polarization is just vertical polarization is when the conductive elements are oriented vertically. So just as shown here, like you're looking at this, if you're standing on the floor looking at it, that's what it'll look like. Those elements are vertical. Then you turn it 90 degrees so that the elements are now horizontal. That's horizontal polarization. So again, E plane is in the direction of the elements, and the H plane is orthogonal to that. So again, going back to our diagram, our general setup diagram here, where we have if we common mode energy from our EUT couples onto these cables, we get a common mode current on the cable that can produce radiated energy, and incident radiated energy will couple onto that cable that can be carried back into the EUT. Well, we'll introduce or review our lossless transmission line model. All of these cables above the ground plane will behave as a cable or wire above ground transmission line. Okay, so if you look at the cable and then the ground plane, you have to think of them as a transmission line as you go up in frequency. And so the current that's actually the current that you really more readily think about that's traveling along the direction of the cable, that's going to be the horizontal component of your current. Okay, but then you're also going to have this displacement current flowing through the capacitance between the cable and the ground plane. So you're going to have a horizontal and vertical component to your currents. So that's going to produce, the horizontal current is going to produce a horizontal component of your radiated electric field, and the vertical current or the displacement current through the capacitance, that vertical component of the current will produce a vertical component of your electric field. Okay, so horizontal and vertical current components produce horizontal and vertical electric field components. And that's why we do separate measurements of horizontal and vertical polarizations when we're using a linearly polarized antenna, like the one we were just talking about, like that dual ridge guide horn. I'll go back to that image for just a moment. Yeah, so so this is why you do this measurement in vertical polarization to get the vertical component, and then you turn the antenna 90 degrees to get the horizontal component. So this is why we do this, because we know that they're going to be, well, just any emitted electric field is likely to have both components. So we need to do those two separate measurements when we're using a linearly polarized antenna. Then here's this statement from the mill standard. The requirement that the first 2 meters of each interconnecting cable associated with each enclosure of the UT be routed parallel to the front boundary of the test setup is intended to ensure that radiated emissions and susceptibility testing properly assesses the performance of the EUT. So again, chapter and verse in the mill standard. The cable layout is a very important part of the general test setup, specifically for evaluating radiated emissions and susceptibility. So when you see this, that we want at least 2 meters of cabling routed along the front edge of the ground plane, it's specifically to facilitate radiated emissions and susceptibility testing to make sure that we're energizing the cables as much as the EUT itself. Okay, so some key antenna parameters I'm going to go into here in this next portion. This is a review from the dipoles session, and this is very high level. Even in the dipole sessions, you know, it was a pretty high level review. I didn't plunge into all the mathematics and the theory behind that. It's just enough to be able to apply this stuff to EMI testing. But we'll talk about directivity and gain, 3 dB or half power beam width, and then effective aperture, effective height, and antenna factor. These parameters are generally available on antenna data sheets. Certainly, you know, EMI test antennas. So ETS Lindgren website has the data sheets for all these antennas here. So directivity is defined as a function. It's a function of direction. So no, my apologies. On the original charts I took these from, I had more of a context for these directions here. But theta is the angle from the axis of the antenna. So in this direction, and then phi is in the direction coming out of the page here. So if you think of the third dimension, it would be wrapping in a circle around this. So around our dipole here, it's basically going to be symmetric about phi. But strictly speaking, directivity is a function of direction of theta and phi, and it's defined as the ratio of the actual power density in a given direction divided by the power density of an ideal isotropic source transmitting the same power piece of T. So you're applying some power piece of T to your transmitting antenna. The power density at a distance r from the source is just going to be your transmitted power divided by the sphere, the surface area of that sphere of radius r, 4 pi r squared. So the directivity is just defined as the ratio of the actual power density in this direction to this power density from an ideal isotropic source. Okay. So numeric is the numeric value of directivity is what I just described. And then we generally express it as dB above isotropic. So it's just 10 log of that power ratio. We're talking about power numbers here. So it's 10 log to base 10 of that power ratio. So that's directivity, and it's generally given as a single number at the maximum value foresight. If you just say it's got a directivity of 10 dBi, whatever it is, that's generally referring to the maximum directivity at boresight. So some notes and cautions. Directivity is sometimes and lazily used interchangeably with gain, G. And I'm as guilty of that as anybody. But they are related, but they're distinct. Gain is the directivity multiplied by the efficiency terms. You know, your loss in the radiating structure, impedance mismatch, and so forth. So that's sort of what I was talking about with the biconical antenna. The biconical antenna is not very directional, but it has very low gain at the low frequencies because it's very lossy. So it's just important to keep these two concepts. They're related but distinct. Directivity is, as I just described, is all about the directivity of the beam, where gain includes these other factors like losses, impedance mismatch, and so forth. So in a lot of cases, you can kind of get by with interchanging the terms, but you know, just bear in mind that they are different. Different symbols are used in different texts. So you know, like for the efficiency terms, that is, like they'll use E. Well, we use E as our exponential as 2.718, so forth, or eta, which we also use for impedance. So I'm just showing them here that you might see these different terms, but just pay attention to context. Okay, so anyway, that's as much as I'm going to say about that. So half power or 3 dB beam width. This is an important one that we use all the time. So the 3 dB beam width is just defined as the angle between the two directions in which the power density is 1/2 or 3 dB down from the maximum power density of the beam, generally at boresight. Okay, that's how we define beam width. It's just at what angles from boresight are we half the power at boresight. So it's clearly inversely related to directivity. The more directive a beam is, the smaller that angle will be. So effective aperture is one way of describing how we convert an incident energy from an incident, or power from an incident electromagnetic wave, into a signal that the antenna then provides to its downstream circuitry. So if we look at this in terms of power, you have an incident power density of your incoming electromagnetic wave, so power density in watts per square meter. And then your effective aperture is going to be expressed in typically in square meters, could be square centimeters or what have you, but typically square of some dimension, right? So square meters in this case. And so that incident power will be multiplied by this effective aperture. So your watts per square meter will be multiplied by your effective aperture in square meters to give you the total received power delivered to your receiver or amplifier or whatever, but your downstream circuitry. And the theoretical maximum value for effective aperture is given by this expression, the gain, and this is actual gain, not directivity, but gain times the square of the wavelength over 4 pi. So another way to think of this, and this is more typically how EMI test antennas.
Bothers you, sometimes I don't throw headphones on because I'm moving around.
Their question.
If it's you're doing something you need that quiet, just let me know and I'll put headphones
Can you please
on.
mute? Got a hot mic there. Okay. So another way to think about this is you'll have an incident electric field in volts per meter. Okay, and so for a uniform plane wave, this is the relationship here. The power density equals the square of the electric field divided by the wave impedance. So in air or vacuum, that's 120 pi or 377 ohms. So the effective height is what you would multiply that incident electric field in volts per meter. You'd multiply by the effective height in meters to get the received potential. Then is delivered to your downstream circuitry. Okay, and so the antenna factor is the reciprocal of the effective height. The antenna factor is what tends to be used by measurement equipment or software to convert the measured potential back into the incident electric field. And it's generally expressed in dB per meter, or sometimes dBm to the -1 power. You got to be careful how you express this, because dBm is how we typically express power, at least low-level power numbers. So, dBm to the -1 should be pretty clear, but I generally prefer to show it as dB/m, because then it's very clearly distinct from dBm. So if we look at how to relate the antenna factor and the antenna aperture that we just talked about, well, so the antenna effective height is defined as the coupled potential, the ratio of the coupled potential to the incident electric field. That's just the definition of effective height. And then the antenna effective aperture, we use that theoretical maximum, the g lambda squared over 4 pi. Well, then we just convert lambda to c, speed of propagation divided by frequency. So we get this alternate expression here, gc squared over 4 pi f squared. Then in a 50 ohm system, just assuming we've got a 50 ohm receiver, which is typically what we got, then our received power is going to be the square of the received potential divided by 50 ohms. And then our incident power density is just the square of the electric field divided by the wave impedance of 120 pi. Then we can set our effective aperture, just this expression here, gc squared over 4 pi f squared. We just substitute our received power divided by our incident power density, right? These two expressions here, and it's just algebra, right? We just rearrange terms. And then we take the square root of v squared over e squared. Well, v over e is our effective height. Okay, and just simplifying this expression, we get this equation here, and so we take the reciprocal of it. The reciprocal of effective height is our antenna factor, and then if we convert that to dB, we get this expression here. So you'll sometimes see this, you'll sometimes see me use this when it just comes from this algebraic manipulation. You can look through that when I make the charts available. But the theoretical antenna factor is given by this 30.22 times 20 log of the frequency in gigahertz minus the antenna's gain in dBi. So the antenna factor is used to convert the measured potential at the receiver into the incident electric field. Right? Your measurement receiver just knows what potential is it seeing, and then you have to provide that antenna factor to get back to the measured field. Data sheets will generally provide the antenna factor directly, or when you have them calibrated, you should get that factor directly, and that can be entered directly into your measurement system software. Now, if you don't have it, you can derive it from the gain. Sometimes you will only get a gain number if the antenna factor is not provided directly, but you can back out the antenna factor from the gain using this expression here. So the way I like to describe this is first, if you're working forward, right? If you're just looking at, when I say working forward, working in terms of how the energy is propagating and turning into an electrical signal that you can measure. So you have an incident electric field, okay? And then that is being converted into a voltage, into a potential that your downstream circuitry will then measure. And that's the conversion between the electric field and the potential is the effective height, okay? So just numerically, it's E times H sub B gives you voltage. Or in dB space, it's an electric field in dB microvolts per meter plus the effective height in dB meters gives you the potential. But and this is kind of a key part of one of the sections of my test and measurement presentation. When you're making a measurement, you're really working backwards, right? Your starting point is really the end point of the signal chain, right? This is all you see. You see this measured potential, and then you could even say it's going further downstream through other signal stages or what have you. But all you have is the end point. You have this potential that you can observe and measure, but then you have to work backwards to determine what was the quantity of interest that gave me this potential. So if I have a potential that I'm measuring, I have to divide by the effective height to get the electric field that caused it. So in dB space, I'm taking my measured potential and then subtracting the effective height to get to my electric field, just strictly numerically and theoretically, right? But for whatever reason, the standard, at least that I've seen, most measurement software, pretty much all measurement software I've dealt with, expects a number to be added to the measured value to get to the electric field. They don't like subtraction for whatever reason. If anybody actually knows the reason for that, I'd love to hear it. But I think that's just a standard that was set up some years ago. We don't like subtraction. We want addition. We want a number that we add to our measured potential to get back to the current. That applies, to electric field. That applies to current probes as well. That's a subject of a different conversation. But so there we go. There's our antenna factor, which numerically is simply the reciprocal of the effective height. And then in dB space, the antenna factor is just the negative of the effective height. Okay. So then that becomes the number that you can add in dB space. That's the number you can add to your measured your measured potential to get the electric field that caused it. Okay. It seems pretty straightforward, but it is a really remarkably easy thing to get wrong. If what you have is the effective height, and that's what you enter into your measurement software, you're going to get very goofy results, right? So you need to make sure that you're entering the number into your measurement software that it's expecting. Right. so that you're getting out there, you're getting a meaningful result. Okay. So as I said, many of these antennas will provide you the antenna data sheets will provide you the antenna factor right on them. So here's a typical antenna factor for the 3115 double ridge guide antenna, and it's dB per meter, or in this, they express it as dB meter to the -1. I like that they put this in parentheses just to really make it clear that you're not talking about dBm, because your eyes might miss the -1. So anyway, this just shows that you're down around 25 dB per meter at the low end here at about a gigahertz, and then it increases accordingly above about 10 gigahertz. So this is the small dual ridge guide horn. That goes from 1 to 18 gigahertz. Okay. So we look at a basic measurement setup. This comes from my general purpose test and measurement presentation. But if you're making a current measurement, right? So you start with a current probe, or if you're making an electric field measurement, you have a test antenna, right? So one way or another, you have some signal that's producing a voltage at the output terminals of the device. And then ultimately you're getting to your measurement device, an oscilloscope or spectrum analyzer, EMI receiver, what have you, that's ultimately tapping off some potential at its input connector. Well, you're going to need a cable to get you from your your transducer to your measurement device. And so the cable is going to have some loss associated with it. Now, at low enough frequencies, the loss is generally pretty negligible. It kicks in maybe around a couple hundred megahertz, depending on your cables. But in general, you need to pay attention to this. And then you may have a preamplifier if needed, if you're measuring very low level signals. And so there'll be some gain associated with that preamplifier. So, and then that will give you this measured value at your measurement device, whether it's in dB microvolts, dBm, or whatever other unit you prefer. So here again, I find it helpful to at least conceptually think of it in terms of working forward first. Right, you start with your quantity of interest, which is the actual current or electric field, right? That's the thing you're trying to measure, the thing you are measuring, the thing you are measuring deliberately, right? Then you add the transducer's transfer function, so it would be the transfer impedance of your current probe in dB ohms, or the effective height in dB meters for your antenna. Then you would add your gain terms and then subtract your loss terms, and then that gives you the quantity of interest, right? So that all should make intuitive sense, right? Remember, you're in dB space, adding is equivalent to multiplying in numeric space. So like you're multiplying by your gain, or you're just adding whatever that gain is in dB, you're subtracting the loss. That all makes intuitive sense, right? Everybody with me?
Yep, we're with you.
Okay. So then you have to flip that around, because again, you're working backwards, because you're starting with your measured value. So then you have to add your loss terms and then subtract your gain terms. And I'll harp on this because it's important. At least I think everything in here is important, right? But anyway, let's say you have 20 dB of loss. Well, that means that the actual value that you have at the input to the cable, if your cable has 20 dB of loss, that means that the actual value here at the input side of the cable is 20 dB higher than what you are observing at your measurement point. So you have to add that loss back in to get what you really had here. Same with gain. If you have 35 dB of gain, I think that's really typical value for one of our LNAs we use for radiated emissions. If you have 35 dB of gain, then the actual signal level at the input to the preamp is 35 dB lower than what it is at the output. So I just point this out because it can get very confusing, and it certainly threw me the first time we, just as I was getting a handle on this whole test and measurement thing, like, why are we subtracting gain? Like, you add gain? Like, well, yes, you do when you're working forward, but when you're working backward, you have to flip all those things around. Your loss terms are what you add, and then your gain terms have to be subtracted, which means also means you have to make sure you're entering those parameters into your measurement software with the correct sign. Right? If you're doing this sort of thing by hand, and I've done it this way where I put all of the numbers in terms of gain. So like any gain in my preamp is just a positive number for preamp gain, but then for my cables, the loss will be a negative number. Right? I put it all in terms of gain just to help me keep track when I'm doing it by hand, like if I'm entering numbers into a spreadsheet or something like that. But if your measurement software, is wanting those loss terms as, just as a positive number, it's 20 dB of loss, it's not negative 20 dB of gain. You need to make sure that you're entering in those numbers correctly, right? I mean, loss should just be a positive number, and gain will probably prompt you for a positive number as well, and it should do the subtraction accordingly. So anyway, so you just got to really pay attention to what your measurement software is, how it expects those terms to be entered. And then you add your transducer factor. So whether it's a probe factor for your current probe, right, in dB per ohm, dB over ohm, dB ohm minus 1. So the reciprocal or the inverse of the actual transfer impedance, or the antenna factor in dB per meter. And then that gets you back to the quantity of interest. So just test and measurement. That's why I have a whole separate presentation on it. It can be a very tricky thing. It's what we depend on, right? We take measurements all the time, but you just have to pay attention to all these different things because you're almost always measuring you're almost always measuring something indirectly, right? I mean, clearly you're several levels removed from the actual quantity of interest. All you know is what you're measuring here. And then you have to account for all these different things in your system to get back to the quantity of interest. And you just have to pay very close attention to how your measurement software is doing those conversions, not giving you some goofy result. And that is where this measurement system integrity check comes in. That this verifies all the stuff that I've just been talking about, that all your parameters have been entered correctly. You put a known signal in this case for radiated emissions, you basically tap off the antenna and then you provide a known signal at that point in the signal chain. So then it verifies that you've entered all those parameters in correctly. So that you're making an assumption about what's coming out of your antenna. You don't have a way of backing out. Like you're not. The ideal way would be to provide some known electric field here and go through the entire signal chain. That's not very practical, and that's non-trivial to do. The next best thing is to provide a known signal in the signal generator to the point where the antenna connects to the rest of your signal chain. And then this verifies that if you apply all those factors and get the equivalent electric field within plus or minus 3 dB, then you've entered in those parameters correctly and you can proceed with your measurement. This is another thing that we really should not be eliminating this from our test plans. Sometimes people say, we'll try to, let's save time, let's not do those measurement system integrity checks. And that's really not a good idea, because you need to have this stuff and you need to have these things recorded in your test plan to go back to be able to verify that you can have confidence in the measurements that you took. Because it's happened more than once where somebody will question the validity of the measurements. And if we can point to the measurement system integrity check saying, well, we did this just before taking the real measurements, and for this reason, we think we have some confidence in these measurements. And it's a very important step. Don't leave it out. Okay, everybody with me so far?
Yep, go ahead, John.
Okay, so what is this thing called far field? So again, this is review from the dipoles session and probably one or two other sessions. So recall the point source approximation, and hey, it looks like my animation's working. That in general terms, you can consider yourself to be in the far field from when you are at a sufficient distance from the source that it can be approximated as a point source. And the significance of that is that the energy will propagate outward as an expanding spherical wave. I'm just showing two dimensions here, so it's an expanding circle, but you can use your imagination. It's an expanding spherical wave. And then if you go further still from your source, and you're only looking at a small portion of that spherical wave, then you can approximate that as a uniform plane wave. And then the mathematics and the general concept gets a lot simpler. And what that means is that you have a uniform power density and field intensity and phase across the surface area of interest. So if I'm at some given distance from my source, and if I'm truly far enough away that I'm in that part of the far field where that wavefront is truly a uniform wavefront or a uniform power density and field intensity, well, I can put my receive antenna anywhere along that wavefront and get the same result. Right. So it's a bit more forgiving as long as I know I'm at the same distance from my measurement or from my source, I can have a bit of slop in where I put my measurement antenna and get the same result. So that's the ideal. That's when you're truly in the far field. For RE102, we are not. When you have an antenna with significant dimensions that is 1 meter away from a source, you are not in the far field. Right? That wavefront is not uniform over the antenna aperture. It is still looking like an expanding spherical wave. And so the antenna factors are calibrated specifically for 1 meter measurement distance for these different measurement antennas. And 3 meters and 10 meters are also typical measurement distances for commercial applications. But pretty much for everything we do, it's the 1 meter measurement distance, and those are the calibration factors we should be using. So if you use other measurement distances or using the incorrect antenna factor for, say, a 3 or 10 meter distance, it will introduce measurement errors. So this is just a quick pictorial illustration, right? As opposed to a non-pictorial illustration. It's an illustration of the significance of being very specific about that 1 meter measurement distance, right? If you just say, oh, I'm going to move it back to 1.5 meters or what have you, that calibration, that antenna factor calibration number that is specific to 1 meter is going to be less accurate if you muck with that measurement distance. Now, is it terribly significant? I don't know. If it introduces 1 or 2 dB error in your measurement, and you're aware of that and you can tolerate that kind of uncertainty, then maybe it's okay. But again, it's just being mindful of your application. Right. So, but this is why that 1 meter measurement distance is very specific and is a non-negotiable. You got to keep to that 1 meter. So some alternate antennas, log spiral and log periodic. These are a bit controversial, but hey, I always like to bring these up. So these types of antennas, they have a lower and constant gain as a function of frequency, or nearly constant, right? As a function of frequency, which translates into a wider and more constant field of view. Okay, if it's lower gain, it means its beam width is wider. So you can look at more of your test article with one antenna position. So if you've got a large test article, especially like a system level test, it can make much more efficient use of test time if you can significantly reduce the number of antenna positions you need. So they're better suited to capture all of the radiated emissions from a given test setup using fewer antenna positions, reducing total test time. And there's a particularly significant advantage when performing a radiated emissions test on a larger test article, such as an integrated instrument, payload, or spacecraft, when costs per test time are significantly higher due to marching army costs. Okay. So log spirals in particular, they are discouraged in MIL standard 461G, but they are specifically encouraged for space station application in the associated documents for state ISS testing. They are permitted on Goddard platforms. And it's project specific, right? I mean, if some projects don't want to use them, well, then we don't have to. It's just another option. But the wide field of view, or low gain, equivalent to saying low gain, and circular polarization enable most measurements to be completed using only one position and one polarization. So you save on antenna positions, and you don't have to use horizontal and vertical polarization. You just get everything with one position. And that is a little more typical for some of the antennas used on spacecraft. That they tend to be more circularly polarized. So they can offer significant time savings, particularly for a system level test. So a few logistical notes: the log spiral antennas are circularly polarized, which means their response to a linearly polarized wave is going to be 3 dB down from what it will be for a proper circularly polarized wave. So you have to address this in one of two ways. You can apply a 3 dB correction factor, or minus 3 dB correction factor to the test configuration, or subtract 3 dB from the nominal limit. Okay, so one way or another, you just have to account for that. That if it's a linearly polarized wave, what comes out of the circularly polarized antenna is going to be 3 dB down from what it would be if you were actually measuring a proper circularly polarized wave. Okay. So,
Hey, John.
yes, sir.
Yeah, this is Ed. I've sort of encountered this I don't know, controversy in the past at Goddard. Some projects do and some don't. How is this determined? I've always wondered. Is it by the lead EMI guys or a person's past history? Is it personal thing? How's it done?
It's project by project. I personally don't have any problem using them. I know for all the reasons that I've cited, but if a particular project engineer just really doesn't want to have to deal with some of these factors and just decides not to use them, I mean,
So it does boil down to
the
the EMI lead's call for that project and some kind of project call.
Yeah.
Okay.
I mean, some people are just not as comfortable with some of these uncertainties or just deviations from, I guess, just normal behavior for a linearly polarized antenna. And it just, it means you will be adding test time, but so it's just adding test time, but not necessarily, it's not a technical issue.
Yeah. Okay. Thanks.
There's one other factor. The low gain of the log spiral antenna may not have the required sensitivity in the notches, depending on the level of the notch. If so, it is recommended that a basic sweep be performed using the log spiral, then go back and scan the notch frequencies with the double ridge guide horn. And notches are what we're going to talk about here, I believe, next. We're coming up very shortly. So yeah, if you've got a very low level notch, you just may not have the sensitivity. I mean, that's it's low gain. It doesn't have much sensitivity, so you may need to go to a higher gain antenna to measure those notches. Okay. So antenna positions. So MIL standard 461 specifies the following for RE102 antenna positions. And I'm just going to read this verbatim because this is important. For testing from 200 megahertz up to 1 gigahertz, place the antenna in a sufficient number of positions such that the entire area of each EUT enclosure and the first 35 centimeters of cables and leads interfacing with the EUT enclosure are within the 3 dB beam width of the antenna. And for testing at 1 gigahertz and above, place the antenna in a sufficient number of positions such that the entire area of each EUT enclosure and the first 7 centimeters of cables and leads interfacing with the EUT enclosure are within the 3 dB beam width of the antenna. So again, all cables connecting to the EUT are considered part of the test article. So clearly, above 1 gigahertz, it's not quite as stringent, right? You only need to have the first 7 centimeters of the cables and leads within the 3 dB beam width of the antenna. The above 1 gigahertz, the wavelengths are shorter and so forth. But below a gigahertz, you need to have the first 35 centimeters of cables and lead, within the 3 dB beam width of the antenna. So you just got to pay attention to that when you're defining antenna positions. And it's just basic geometry. Spot size is determined by the 3 dB half power beam width of the test antenna. And so just a couple of examples. When they specify that 3 dB beam width, it's the full angle from one point to the other across the bore sight line. Right? So the spot diameter that then is you take that angle that they'll give you in the data sheet and you divide it in half and then take the tangent of it and then multiply it by 2, right? The tangent gives you this dimension here from the bore sight to the edge of the beam. And so you multiply by 2 to get to the full beam width. And then this factor of R, this actually is more applicable for radiated susceptibility where you have some flexibility. That'll be what we cover next in a different session. In radiated susceptibility, you can move the antenna back if you've got enough amplifier power. You can move it further back than 1 meter to get a bigger spot size. And radiated susceptibility is a much more time-intensive test. So reducing antenna positions is much more desirable for RS because you will significantly save test time a lot more than with RE. It's still a good idea to do with RE to be most efficient. So for RE, this R is just going to be 1 meter. Okay, but it's just basic geometry, right? So for a 30-degree spot size, and you just work through the numbers here, the spot size is a little over half a meter, and for a 60-degree beam width or 3 dB beam width, your spot size will be a little over a meter. Okay, so a 60-degree beam width that's pretty good. A 1 meter spot size for a box, for a box level test, it is pretty good. That should get you most of the way to what you need to be for a single antenna position. So you know your spot sizes for each test antenna. That allows you to select an optimal number of antenna positions in order to provide sufficient coverage of the UT and interconnect cables while making the most efficient use of test time. So here's an example of the 3115 dual ridge guide antenna. So some data sheets will give you a whole series of plots like this in different frequency ranges. So this is at 3 and 4 gigahertz. So this is really helpful. Then you can just really see this at a glance. Sometimes you'll just get a single graph like this. But here in this data sheet you get both, which is very helpful. But you can just really see visually that your 3 dB beam width is about 20 degrees, or plus and minus 20 degrees, so a total of 40 degrees at 3 gigahertz. So 40 degrees is pretty good, so you get a decent spot size from that. The one thing I'll point out here is that the spot size goes way down above about 15, 16 gigahertz. And if you select your antenna positions, the worst case based on this, then you're going to need a lot more antenna positions. But by and large, we're not really concerned a whole lot. We don't. If you don't have any receivers on your platform operating in this frequency range, I would recommend that you don't define your antenna position based on this beam width. Set it to what's a more nominal beam width across the frequency range of interest. Mostly, we're dealing with receive antennas below about 10 gigahertz. I mean, if you do have something operating in this range, then sure. But again, just use the information that's provided to you in these data sheets so that you can make informed decisions about your antenna position. Then, okay, so here's the lower frequency conical log spiral. So this has, yeah, this one has a 3 dB beam width of 60 degrees, right? Plus or minus 30 degrees. So that's a nice, that gives you a nice big beam. The higher frequency log spiral, also about 60 degrees, from 1 to 7 gigahertz. Now, there's one other thing that I think does make people a little uncomfortable about these. The center of the beam, on at least on this higher frequency log spiral, does shift a little bit above 7 gigahertz. Right, there are different lines here for at different frequencies. So the red one is 1 gigahertz, orange is 7 gigahertz, and the green one is 8. So you can kind of see that the peak, the peak gain is a little bit off axis, kind of significantly off axis at 8 gigahertz, and even at 7 gigahertz, it's moving a little off axis. That makes some people a little uneasy about these log spirals. But I mean, to my mind, it's the bore site gain is just down I don't know, a few dB here. So, you know, as long as you take that into account, you know, I don't think it's an insurmountable problem, especially when you're making these measurements like on a large test article, like at system level. I don't think you're generally dealing with like a 2 or 3 dB level problem at that point. So, but there again, just you know, use the information at your disposal. These antenna data sheets are readily available. You know, just look up the parameters for the antennas that you're using, and make an informed decision about the test antennas you want to use on the antenna position.
Hey, John.
Yes.
Yes, Ed again. Could you go back to the log? Yeah, I've never seen that before. I guess it depends on how the spiral is wrapped, and that center beam has some orientation with respect to that, the way the wrap starts.
I imagine I don't know the full physics of how that antenna operates, but I mean when
Okay.
that's
Interesting.
I mean that model number should be consistently made from one to another. But if you use a different log spiral from a different manufacturer, where maybe the you know, even the circularly polarized antennas, they are like right hand clockwise or left hand clockwise polarized. If another manufacturer, you know, coiled the conductor around in the opposite direction, you know, if you're measuring just linearly polarized signals with this antenna, it shouldn't really matter that much, but it could.
Mm-hmm.
So yeah,
Okay.
yeah, that's about as much as I can really say about that.
Subtleties.
Yeah. All right, so I want to make sure we talk about notches. So
Hey, John.
everybody good so far? This is kind of the last major topic here.
Yeah, hi, John.
Oh, hey, Dependra.
So
Do you have a question?
It looks like these circularly polarized antennas reduce the test time by half, because we don't have to go between horizontal and vertical polarization.
Right.
So are these antennas popular, or so why are not they as popular as I guess
John Lichtig, are you listening?
Yes.
John doesn't like them very much.
Yeah.
Kind of at all. But
Yeah, I think the main reason is misuse. The mill standard, they try to write the document so that the different laboratories can understand how to perform the test correctly. And when they find that there's a lot of misinterpretation, they say they're not allowed. And that's main reason for this antenna not being
Yeah.
allowed by the mill standard.
I could talk to you about that one offline, Dependra. That's kind of a big topic. But I think we generally, if we're going to use them at Goddard, we generally reserve them for like integrated platform level testing, because then the mill standard doesn't really apply to that. The mill standard is applying to component or box level testing. And I mean, in GEVs, I specifically allow for their use in a box level test at the discretion of the test engineer. But yeah, it's I like them for the reasons that I've said, but there are some caveats, and you just have to be mindful of them. Is my general approach to things. But we can talk some more offline about that.
Yeah,
Okay.
thank you.
Yep. Okay, so what's in a notch? Each notch, in a radiated emissions limit, usually you see like the default line from the mill standard, and then you see these notches that make, you had this nice beautiful line. Why did you have to put these notches in here to make the limit more ugly? Well, those notches are there to protect specific receivers, and so they are the very raison d'etre for RE102. Outside of those notches, the limit is essentially arbitrary and not nearly as meaningful. So GEVs, in the equivalent of the application guide appendix in GEVs 253, and that's the specific section here for RE102, provides guidance in defining and evaluating. Try that again. Guidance for defining and evaluating meaningful limits that may be measured within the constraints of available technology. You want to actually be able to measure this stuff, right? And then strategies for measuring to such low limits. So it starts with thermal noise power. The theoretical noise power in watts delivered by a thermal source into an impedance match load is KTB, or K sub B, Boltzmann's constant. 1.38 times 10 to the minus 23rd joules per Kelvin. And then T is temperature and B is the measurement bandwidth. And this is right out of textbooks. Any textbook will provide this number, or this equation, so I'm not going to derive it or anything. But if we take basically room temperature, 290 Kelvin, and then convert to dBm, we get that noise power is minus 174 dBm per hertz, plus 10 times the log of the measurement bandwidth. And then for a 50 ohm system, well, we just add 107 to that minus 174. So we get minus 67 dB microvolts per root hertz times 10 log of measurement bandwidth. Okay, so it's power spectral density watts per hertz. But then when you relate it to potential, to voltage, you basically are taking the square root. That's how you end up with these units of volts per root hertz. I know when I first saw volts per root hertz as a young fresh out, I really had no idea what that meant. But when you relate it to watts per hertz, it makes a lot of sense. So these numbers you'll see again. I mean, commit them to memory, or you'll use them enough that you won't have to commit them to memory. You'll just know these. But that, if my general strategy is I suck at memorizing things. I try to minimize how much I have to memorize. And so if I just remember minus 174 dBm per hertz, then I know that I get the lower number by adding 107 to it. Then all I have to remember is the minus 174. That's the one to really remember, right? Minus 174 dBm per hertz. And so that gives you the basic noise floor of an ideal amplifier, receiver, what have you. Then the noise floor may be further converted, really should be converted into an equivalent minimum measurable electric field level in dB microvolts per meter using the antenna factor. Okay, we talked about the antenna factor previously, but just bringing that up again. You have your noise floor, and then you add the antenna factor to it, and then that's how you get to the your noise equivalent electric field. But one very important note here is do not use the bore site value of the antenna factor from the antenna data sheet. You want to calculate a worst case, you may use assuming a 0 dBi gain in side or back lobes. So on the next slide here, the antenna factor that you're given from a data sheet or even a specification for a flight antenna, right? Something you're going to actually use on the platform. That's for the main beam gain, right? You shouldn't be pointing your antenna, the main beam of your antenna, back to the spacecraft, right? So your whole raison d'etre of RE102 is to protect specific receivers from incidental emissions, and those are generally and should always be in the side or back lobes. So do not use the antenna main beam gain to define limit. Have I mentioned that? Yeah. So in that antenna factor equation from the earlier slide, we generally assume 0 dBi as a worst case for side and back lobes. Now, I'm supporting a program where they have some characterization data from their antenna vendor to show that they've got negative gain more than whatever 20 or 30 degrees off of bore site or whatever it was. Like they can say that, okay, we know we're at least minus 10 dBi of gain for however the antenna is going to point during the mission. So okay, if you know that, you can say unequivocally that it's going to be minus 10 or what have you, then okay, you can use that. But I generally, as a starting point, I use 0 dBi as a worst case. Okay. But you can see I don't have a specific chart on this, but you can see that what you're doing here is you're taking that antenna factor, then you're adding it to your noise floor to get your noise equivalent electric field. Okay. So if the nominal gain you should be using for this antenna factor in this analysis, if that's supposed to be if that should be 0 dBi as your worst case, well, if you're adding some higher level gain, and I'll use a specific example without mentioning any names here, but there's one program I was supporting where the antenna in question was a dish antenna, a high gain antenna, and so its gain was, I believe, at least 30 dBi. We'll just use 30 dBi. So if you use 30 dBi here instead of 0 dBi in this equation, then you're subtracting the gain, right? So then your antenna factor is going to be 30 dB lower than a reasonable value you should be using to determine a notch level. Okay, so your antenna factor is going to be 30 dB too low. And so if that's the number you're adding to your noise floor, you're adding a number that's 30 dB lower than it should be, then you're going to get a noise equivalent electric field that's 30 dB lower than it should be. So you're going to end up with a really ridiculously stringent notch that in the particular case I'm talking about was not possible to measure without breaking the laws of physics. And I went through this analysis with the organization that defined the limit, and the project was canceled before I ever really got an answer to it. So we never actually did get a reasonable redefinition of that notch level. But this is the sort of thing to bear in mind when somebody is applying a really, really stringent notch level. Pay attention to, ask them how they derived it, and did they use main beam gain? If they use the main beam gain of a dish antenna, then the level that they're giving you is probably 30 plus dB lower than it should be, than anything that makes any sense. Okay. So noise factor is just first looking at it as numeric quantity. It's simply the ratio of a device's actual output noise floor to the theoretical thermal noise floor limit, that KTB number that we talked about, okay? And both quantities are expressed in terms of power. So the noise figure, which is what we more typically use, is just this noise factor expressed in dB. So just 10 times the log of the noise factor. Okay, so your noise floor in terms of power is going to be that minus 174 dBm per hertz, plus 10 log of the bandwidth plus your noise figure. Okay, and same expressed in voltage here, the minus 67 dB microvolts per hertz. So a good low noise amplifier, a good noise figure is generally less than 2 dB, less than 1 dB if you can get it, right? So 1 to 2 dB is generally what you want for a good low noise amplifier. So the RE notches must define a level and a measurement bandwidth. The limit is incomplete if they don't specify a measurement bandwidth, and I see this all the time. The level cannot be lower than the theoretical limit for any given bandwidth. And measurements in any notch must be performed with ideally the same bandwidth used by the receiver that is being protected by the notch. The measurement bandwidth is not arbitrary. You don't just define some limit and say, well, just crank ratchet the measurement bandwidth down as low as you need to meet the noise floor. That's not a proper engineering basis for designing a notch limit. Okay. But if you take this is the theoretical antenna factor for defining notch levels. You should use the actual antenna factor if you have it. Again, based on using 0 dBi gain for side and back lobes. And so I get this family of curves for the theoretical limit at different measurement bandwidths. And this tells you how realistic some of these are just notional notches here, but how realistic some of these notches would be for given measurement bandwidths. Okay, so if you plot something like this, and if somebody's giving you a given notch here, let's just say here's your S band is about up here, and if its operational measurement bandwidth is 10 kilohertz, which is fairly typical. Wait, I take that back. I'm sorry. This is a GPS. No, that's not right either. This is about 10 gigahertz. So whichever that is. Okay. If you have this notch and it's supposed to operate with a nominal bandwidth of 10 kilohertz, and this is all just theoretical, you don't have a lot of room here to play with. And this is also assuming 0 dB noise figure. So if this noise level goes up at all, you're not going to be able to actually measure that level, right? That's not a realistic level for that bandwidth. Okay, and then if they just tell you, well, just crank your measurement bandwidth down to a kilohertz, well, that may not be a valid thing to do. That's the next slide here. If you look at just an example of clock jitter, that a clock signal will typical jitter spec, and this is probably a very sloppy spec, right? But let's just go with a clock jitter spec of 50 parts per million. And that's going to apply to all your harmonics. I mean, that's effectively a percentage, or it's a fractional jitter spec, right? So whatever frequency you're talking about, all of your harmonics are going to have that same 50 part per million or whatever the spec is, right? So if you've got a harmonic of a clock landing in your S band at 2 gigahertz, that equates to plus or minus 100 kilohertz. Okay, if your platform receiver uses a bandwidth of less than 100 kilohertz, so say maybe 10 kilohertz, it may not capture all the energy from that harmonic. Okay, so if the measurement bandwidth is used that simulates that of the platform receiver, the measured response will be comparable to that of the platform receiver. But if the bandwidth, your measurement bandwidth is arbitrarily reduced even lower in order to reduce the noise floor, then your measurement receiver will not capture all the energy that may be captured by the platform receiver and may miss it altogether. Okay, if you've got this harmonic landing in the receiver pass band, and if the bandwidth is wide enough to capture all of the, if the receiver is going to be using a bandwidth that will be sufficient to capture essentially all of this energy, even if this frequency is jittering a bit, but then you ratchet down your bandwidth in your measurement to say 1/10 or 1/100th of the receiver's bandwidth, you're going to miss it. You're going to significantly reduce the amount of energy that you're seeing, and you could get a false indication of a pass, which is the worst result. That masks a potential problem that could bite you later in the program. Okay, so the measurement bandwidth is not arbitrary. It must be commensurate with the operation of the receiver that's being protected by the notch.
Hey, John, question there.
Yeah.
So that seems like there's a spec issue with the receiver. In other words, they are advertising or allowing a smaller pass band than can be backed up by the stability of the clock.
Well, I mean, the receiver passband, well, the passband and bandwidth are, yeah, I mean, I guess the bandwidth is related to the passband, but the measurement bandwidth that you're using to make your RE102 measurement in the notch needs to come from the receiver provider. They need to tell you, we are operating with a 10 kilohertz bandwidth or a 100 kilohertz bandwidth or what have you. And the measurement bandwidth should be consistent with that. It's not just we're gonna make the measurement with as low a bandwidth as we can get away with it to knock our noise floor down. So the point is, if the receiver vendor says we're going to be operating with a 1 kilohertz bandwidth, then that's what we need to use when we make our measurements. We need to use that bandwidth when we're making our RE102 measurement. This is just an example of what can happen when you're using an artificially low bandwidth compared to how the receiver is operating.
Just to be clear, when I say receiver, I'm talking about the EMI receiver,
Yeah,
not the flight hardware.
oh, okay. Okay.
So what I'm saying is, if you are attempting to make this measurement, and the EMI receiver allows you to set a bandwidth that's very, very narrow that cannot be backed up by its clock, isn't that an issue itself in how the receiver operates, the EMI receiver?
I'm not sure I understand the question.
All right.
I mean,
I'll take that offline then. Thank you.
okay. Yeah, we can certainly talk offline. But yeah, the measurement bandwidth is something that you configure the receiver with when you're making the measurement, and it should be done through the measurement software or on the front panel, however you're doing it. But yeah, well, yeah, let's take it offline. Okay, so here's an example of just from LCRD from more than 5 years ago, I think. But they were going to have a Ka band receiver, and they did not have a specific frequency allocation yet. So they had just specified not really a notch, but to test over the entire Ka band frequency range, or at least this frequency range of 27.5 gigahertz to 31 gigahertz. So it's a 3.5 gigahertz wide notch in quotes. Okay. Now they specified a 1 kilohertz measurement bandwidth. So that means that you're going to have 250 hertz between frequency steps in the sweep. That's typically how it's set up. That you're going to have your frequency steps will be 1/4 of your measurement bandwidth. So that means you have 14 million frequency steps. So using a traditional frequency swept method, the Mil Standard 461G specifies a dwell time of 15 milliseconds per frequency step. So if you just work through the math, you would have a sweep time of about 58 hours for one. That's about 1 work week plus overtime, right? That's per polarization at each antenna position. So if you're using a linearly polarized antenna, you need to do this twice at each antenna position. And if you have multiple antenna positions, this can easily add up to several weeks for a single notch for just one portion of your radiated emissions test. So one portion of one test of your entire test campaign could take several weeks. So now once you know the actual width of a given receiver, in this case, the K-band receiver, when it's known to be much lower, then you can define the span of your notch to be, you can define that accordingly to be a much narrower notch to make the most efficient use of test time. We do that all the time. Right. Once we know our specific frequency allocation for any given receiver, that's what we test to. Because then it's a much more efficient test. Then obviously it's not real hard to be more efficient than this. So, but in many cases, and certainly here, radiated testing must be performed prior to final definition of the specific frequency ranges of the receivers on the platform. In other cases, the test article is one unit in a large production lot that is intended to be used on a large number of platforms. In such cases, it is necessary to test over the full range of the notch. So this is where we introduce real-time FFT receivers. They use a real-time measurement window ranging from 7 megahertz for older units to 80 megahertz on the latest units. This chart's a few years old now. They make some units that go at least to a gigahertz now. But they have a typical dwell time of about 1 second for each window. So with these types of units with a 7 megahertz window, now you could do that 3.5 gigahertz wide span in about 8 minutes. Or with the 800 megahertz window, like on the Roden Schwartz ESW44 that we own, you can do that in about 44 seconds, so less than a minute. So these FFT receivers significantly reduce the time required for these types of measurements. They're also better suited to detect transient type signals. And traditional frequency swept receivers, you can miss things, right? If a transient occurs in a frequency range that you're not looking at right at that moment, you can miss it. So there are a lot of tremendous advantages to these receivers. And so the cost comparison here, the Roden Schwartz receiver was about $180,000 versus several weeks of INT marching army costs. This is how we were able to get 2 of these units. We have 2 of these at Goddard. We've had them for several years now. Just by working through this math here and going to project management, saying, whenever it's time to do this test, we could take, over a month to do your EMI test, or if we make this investment now, we can do this RE test in well under a day. And they very quickly went from $180,000, what have you been smoking, to how fast can we get one? So, you walk through the numbers and it kind of speaks for itself. And then you can get management on board pretty quickly to say, yeah, that sounds like a pretty good investment. And then you have the machine just here for continued use. That's not always a great selling point for project managers, that they're going to benefit future projects, but it is a significant benefit. Okay. So now I'm going to talk about a peak detector, just quoting from the mill standard here. It specifies that a peak detector shall be used for all frequency domain measurement, emissions and susceptibility measurements. So how do we relate peak to RMS values for noise floor measurements? So this is where this is our discussion of the crest factor, and we have talked about this before, but it's always worth reviewing, I think. So thermal noise follows a Gaussian or normal probability distribution. That's just the general equation for a normal distribution here. Just bear with me, because even though I'm known as the mathicist, even probability and statistics has never been my strong point. This stuff always made my brain melt. But it's worth going back to this because so bear with me just for a few minutes here. So this is our general equation for normal probability distribution. So mu is our mean, and sigma is our standard deviation unit, and it follows what we call the familiar bell curve. Right. So this is our deviation from mean, our x minus mu. Okay. So just a quick discussion of mean and standard deviation. You have a sample set of values, just n, capital N samples. Mean is pretty straightforward, right? You just add them up and then divide by the number of samples. and then you have your sample deviation from mean. So X sub n, you just subtract the mean from that. So that's your deviation. Then you square the deviation. Then the variance is the mean of that square of the deviation. So you get sigma squared. Well, then you take the square root of that variance. That gives you your sigma, your standard deviation unit. So you're squaring something, taking the mean of the square, and then taking the square root. Kind of sounds like root mean square, right? And so for thermal noise, that sigma value is the RMS value of the noise, and we're going to come back to that. So this all comes down to probability of occurrence. So the area under the curve, or under a range of values in the curve, gives you the probability of occurrence in that given range. So it must be taken numerically. I actually looked into evaluating this integral in closed form, and it just, a stat book that I borrowed from a friend. It said, yeah, don't do that. Here's a table in the appendix. Go look it up. So you got to evaluate it numerically, but if you're 68% of the time, you will be within one standard deviation unit of the mean, and 95.4% of the time, you will be within two standard deviation units of the mean. 99.7% of the time, you'll be within three sigma. And then now we'll go to a logarithmic scale. It's the same graph, just on a logarithmic scale now. Well, now 99.96% of the time, you will be within 3.5 standard deviation units of the mean. So what that means is that for any value more than 3.5 sigma away from the mean is just what I call not bloody likely. It's just, for all intents and purposes, not going to happen. So for all practical purposes, we can say that the peak value of our deviation from the mean is going to be about 3.5 sigma. Okay, so recall that sigma from the earlier chart is defined as the RMS value of this distribution. So the RMS value is actually 1 sigma. It's not the 0 line. So long and short of it is that the ratio of the peak value of this distribution to the RMS value is just that 3.5 number. For all practical purposes, right? You wait around long enough, like 100 million years, maybe you'll get a value out here somewhere. But for our purposes, that ratio is going to be about 3.5. Well, you convert that to dB, you get 11 dB. And 11 dB is what is touted as the crest factor for thermal noise. This is where that comes from. So what that means is that the noise floor peak, so like when you're setting your spectrum analyzer receiver for peak detection, like you are required to for mil standard 461G measurements, the noise floor is going to be 11 dB higher than the RMS value. And you need to take that into account when you're looking at at noise floor, and for taking that into account when you're defining a notch limit, right? Because you should be measuring that with a peak detector. That's going to raise the noise floor by 11 dB compared to what you would be using if you only looked at the RMS values of your noise, like if you're looking at the spec sheet. And we'll look at some examples of that here. So right here's an example from well, at least one of the older frequency swept receivers we've used, the Roden Schwartz ESIB. At least historically, they've typically displayed noise at displayed noise floor, or a displayed average noise floor. DANL is what I've seen it as in some other data sheets. I don't know if they use that term quite so much anymore, but DANL, displayed noise floor, and they typically are displaying it as average or RMS values. But right here, they say peak, typical increase relative to AV display to average display is plus 11 dB, crest factor. They don't give you any explanation for where that comes from, but that's the crest factor. So So what's in a notch summary? The theoretical minimum is given by the thermal noise floor. That's your minus 174 dBm per hertz plus 10 times the log of the bandwidth, or minus 67 dB microvolts per root hertz in a 50 ohm system. Right? The measurement bandwidth B must be commensurate with that of the receiver being protected. Then you would add your noise figure, generally less than 2 dB for a good low noise amplifier. You'd need to add your antenna factor in dB, and it's frequency dependent, to get the minimum measurable electric field or noise equivalent electric field. And you also need to add that 11 dB crest factor for measurements with a peak detector, which are required by standard 461. So these are all the things that need to go into a properly defined notch to protect a given receiver. And so when you're given a notch level that looks very aggressive, and I've seen plenty, you go through this analysis yourself, you can go back to the people who define the notch, like, I'm not sure that I can actually measure this. Like the example I gave when people were clearly using the main beam gain of a dish antenna to specify a level. And I'll go a step further here again, as long as I'm not mentioning names. They did not specify a measurement bandwidth for the receiver being protected by that notch. And so I just in course of basically walking through this analysis for that notch level, I just intentionally ridiculously used a 1 hertz measurement bandwidth because I didn't have anything else to go on. And even just assuming a 1 hertz measurement bandwidth, the theoretical minimum I came up with was for my noise floor was still about 17 dB higher than the notch that they were specifying. So, I presented this to them, I think, a couple of times at a few different meetings, and I said, I cannot make this measurement without breaking the laws of physics. There is something that I'm missing here. I said, please tell me how you would make this measurement, or if there's something that needs to be adjusted in how this limit is defined. But right at the moment, I don't see how I can make this measurement without breaking the laws of physics. So these are good tools to have at your disposal, at your fingertips, when you're given a very aggressive notch, so that I wouldn't even necessarily call it pushback. I would just say have a discussion with the people who define the notch, because they may not have put all the necessary thought into defining it properly. And they might not be really receptive at first when you show them your results, but if you walk them through the logic and the reasoning that, well, you have to have this, you have to have this, and blah blah blah. When you get beyond the initial recoiling that they're being questioned, I think you can get down to the point of your engineer is trying to make sure that you're defining a proper limit that actually makes some sense. Because it's not really in anybody's interest to have something defined that's 20 dB or 30 dB below the noise floor that you can actually that can be physically realized. Right? And that is what I have. Oh wait, actually that last bullet is what I just said. So all right, that's what I have. Anybody have any questions before we adjourn?
So, John, I put a question in the chat.
Yeah.
Did you see that?
I'm not generally looking at the chat while I'm going through this. Let me see what you got.
So we settled on using the spacecraft antenna for self-compatibility to look at the notch versus using the horn, which we're going to use for the launch vehicle, radiated emissions, and radiated susceptibility. So that goes to when you were talking about the circular polarized antenna. And
I believe that the antennas on the platform on that platform are circularly polarized, right?
yeah, yep. And so kind of gets interesting associated with, okay, I'm going to use the actual spacecraft antenna to do my notch testing at the spacecraft level versus using a horn, which I got to do for the launch vehicle. We got to do for the launch vehicle type emissions and susceptibility, right? So
Mhm.
just a contrast there about how things can be done. That was it.
Okay. Well, and we'll be talking some more about that. I'm
Oh,
still
yeah.
still supporting GeoXO for another couple of months. Yeah, anybody else have any questions or comments? Okay, well, thank you all for participating, and I'll let you know if we're able to do the lab session on Wednesday. Otherwise, I'll make alternate arrangements. We'll maybe cover a different topic on Wednesday if need be.
Thanks.
Okay, have a good day. Bye.
Thank you, John.
So long.